Well, hello and welcome back to this latest video. In this video, which is a continuation where we had a look at the repeater card from 1986, 1987, we had the thing wired up and we had a bit play with it up with the radios and everything, and it's all working completely fine, which is brilliant. But in this video, we're going to look at reading the code from the Eprom. This is the Eprom here. It's a 2716. So in this video, we're going to remove the chip and put it into a reader. Here's a reader here. This is a MiniPro. These are available on eBay, and they're not too expensive. There's actually a Mark II version of this now. This is the Mark I version. It has a ZIF socket on here, a zero insertion force socket with a little lever, there that you can operate. And the idea is you can put take the Eprom off the board, put it into here, and this connects through a USB socket, and that goes to the computer, and then you can read in the data that's on the chip. So first thing to do is to remove the chip. I'll do that now using this little spiky thing I've got here. Okay, so that's the chip removed. I'll see if I can get in on that a bit better. So that's the Eprom removed, and you'll see it's got a little glass window on the front. It's actually not glass, it's quartz, and the idea of that is that you can put this in underneath a high brightness ultraviolet light of the correct wavelength, and it will erase the chip. So unlike chips these days where they can be electrically erased, you don't need any of this business with the quartz window or anything, or ultraviolet lamps. With these chips from the 80s, and they were used right through into the 90s and possibly even 2000 before they started to phase them out, these have to be erased by ultraviolet light. So that's what the window's for. This has got code on it, as I say, and that's what we're going to try and reverse engineer and disassemble. So the first thing would be to put this into the ZIF socket, and that just drops in there like that. And you notice it's completely loose and easy to move around. There's no pins to bend or anything. There's no force required, which is why they call it a zero insertion force socket. That's the whole point. Close the lever, and now that is now in and will not fall out. So that then connects to the computer, and then we can read the data and take it from there. So now let's flick over to the PC, and let's start reading the data from the chip and having a look at the hex code within the Eprom. Okay, so here we are on the desktop, and we're going to start reverse engineering, or looking at the code from the repeater. So the first thing we need to do is to load in the information from the Eprom, and what I'm using here is MiniPro. This is an Eprom reader writer. It works with a hardware interface which communicates through USB. Now what I've already done is, just to save another camera shot, is I've already read the information from the chip, and we've got it saved as a file. So all I need to do is basically open the file, and it's this one here, G0BZY repeater 6502 fixed size .bin. So we need to select that and OK to that. Right, now if we scroll down, we should see some information down here. I'll just zoom in a little bit. You can see we've got like lots of raw hex down here, and at the top of the file it's all FFs, which basically means it's clear. There's no information in there. So you can see that there's a lot of unused space on this chip, pretty much the first half of the chip. Incidentally, it's a 2716, which is a 2K by 8 Eprom, so it's 2 kilobytes of memory, 2K by 8. So pretty much the first 1K is empty. We don't really use it, and it's only when we get, I don't know, 3/4 of the way through, something like that, we start to get information. This is actual instructions which are executed by the 6502 microprocessor, and it starts here at address 600. So as you can see, we've got some information here, and this is straight from the Eprom. We've got no documentation, if you remember, so we've got no information. So this is really all we have software wise. This is it. So the whole purpose of this is to try and reverse engineer what we have and try and get it back into a human readable form, because as you can see, this is very difficult to understand. It's just a load of hex digits. It looks like a lot of random numbers basically, but you know, we can actually work through this and end up with some readable source code at the end of the day. And this is the first step, is just to look at the actual information straight from the 2716 in hexadecimal format. So this first instruction here is A9, and it has a data field of 00. Now I happen to know what this one means. So A9, you could look it up in the 6502 instruction set data book, and you will see that it means load immediate into the accumulator. Well, the accumulator is an internal register within the 6502 chip itself. It's like an 8-bit data register. It's quite small, just 8 bits long. So this means, in computer speak, it means load in whatever's here, which is the data field, into the accumulator. So the data field here is 00. So these two bytes work together, and this means put 0 into the accumulator. That's all that's doing. Right, the next byte would be 8D with some data after it. So 8D means store to a memory location. Happen to know that one as well. I don't know the rest, but that's basically from memory. That's all I sort of carry around in my head. So you'd have to look them all up to decode the whole thing. And the data fields here is 0020. Now this is an address, this 0020, and because it's a 6502, the way that it happens to work is the address fields are reversed. So it's not address field 0020, it's 2000, 2000 if you like, in hex. So this means store whatever's in the accumulator. Remember, we'll put 0 in there. Store whatever's in the accumulator and put it at address 2000. Doors are back to front, and so on through the program. Now you could actually do this completely all by hand and work your way through it. It would take a long time to decode the whole thing. You know, you're looking at a day's worth of work at least, probably just to go through the whole thing and look up all of the mnemonics from the 6502 datasheet and actually figure out what all of these bytes are doing. However, we do actually have the information here, and that's what's important. You'll notice we're at the end of the table here, so where it says address 7F0, that means the very end. That's this address here, 7F0, and this is the very end, which is 7FF. Now remember, it's a 2K chip, so 7FF is actually the last byte, so of the chip. So this is the very last byte in a 2K chip, and you'll notice there's some zeros here and some other bits and bobs. Well, these are the interrupt vector positions. There's a one for IRQ, which is interrupt, and there's one for reset, which is this one here, reset vector, and there's another one for mask interrupt. So we're not using those two, but we are using this one, which it's marked as 00FE. You can see there. Now these two work together to form a 16-bit word, if you like, and that's a 16-bit word, and this is a 16-bit word. So these two are the ones we're interested in. This is the reset vector. What happens is when you get a pulse at the chip, at the 6502, to give it a reset signal, and in our case we'll have a little CR circuit, a little capacitor resistor, which gives a little burst of signal, if you like, on switch on, and it lasts about 200 milliseconds. It's pretty quick, but it's enough to activate the chip and give it a reset signal. So when that happens, the first thing the chip does is look at these two positions here and say, okay, I'm going to jump to position, it's actually reversed, remember, so it's FE00. So in location FE00, in the entire scheme of things, the whole memory map of the repeater design, the memory map will take that to the start position of the code, and it's the first code it will actually execute. Now, it's slightly confusing here because you look at the addresses here and you think, well, there is no FE00, and that's because these are relative addresses to the chip itself. So it starts from 0, if we go to the top, starts from address 0, and when the chip is inserted into the circuit and it's decoded through a page decoder, this will actually start at F000, or is it F800, I don't know, but anyway, it'll start beginning much higher up in the address space. So what you're seeing here is just the relative addresses for the chip itself starting from 0, but in matter of fact, when it goes into the circuit, these addresses will be decoded up to, so that'll start, this byte here would be FFF0, and that would be FFFF, which is the very top of the 64K address space that the 6502 can handle. Okay, so yeah, it looks a bit strange, but that's kind of how it works. What this means is, back to the reset signal, when we get this reset signal, it will take us to the beginning of the code, which is here. This byte here, the one we were talking about earlier, our relative address of 600, and it will execute this code starting from A9, which, as you remember, is the load immediate and all of that. So that's the first thing that happens when you get a reset pulse. Now we can tell that just by looking at this raw data, because we know what these 6 bytes are for. As I say, there's a word there for an interrupt vector, and then you've got a reset vector, and then you've got a non-maskable interrupt vector there. We don't use those two, just the middle one in this particular circuit. Okay, but other than that, it's quite difficult to see what's going on. We know the start position, we figured that out from the reset vector, but we don't really know much else about what the program's actually doing, and that's the problem. So what we need to do is take this to the next level, which basically means run the hexadecimal code that we have here, or the binary file, and run it through a disassembler. Now a disassembler will take all of this hex code and try its best, there are limits, but it will try its best to convert it to a new readable form, or something better than what we're looking at here anyway. So let's do that right now and run it through the disassembler. So let's close that. Now what I'm going to do here is use a program called 6502 Bench, which is, I believe, a suite of programs. You have this one here, which is SourceGen.exe. Okay, let's execute that. Yeah, 6502 Bench SourceGen. This particular version is 1.8.3, which I think is the latest version at this time. So let's start a new project, and from the new project window you can see we've got a selection of options. These are all different types of computer that use the 6502 processor, which is quite nice if we were doing some work with Apple, like the old original Apple, like the Apple II and what have you, or if we were working with an Atari 800 or something like that. These all use 6502. So, and there's Commodore, of course, which is probably the most famous out of all of them for using the 6502. I personally started on the VIC-20 and then progressed to the Commodore 64 later, and at one point I even had a PET. So these all had 6502 processors in them. But what we're going to do is, because ours is it's a purpose-built board that we've designed ourselves, so we're going to go for the generic 6502, which doesn't assume anything about locations or memory addresses or anything. You basically have to set it up all yourself, which is what we'll have to do anyway, because it's a custom board. So let's select the file anyway, and let's load in our binary file. Now if you remember, from the mini programmer, we use this file here, which is G0BZY6502 fixed size.bin, and it's the same file. So let's just open that file again, okay, and then see what we get. Right, I'll just navigate around a little bit. Now from this you can see it's loaded in the data here. Here's all the hex down the side here, and we have some other bits of information that we didn't see before. all this kind of business. So it's DD1, and then we can scroll down and eventually probably start to see something. So anyway, what this program can do, which is all very clever, is you only need to tell it the very beginning of where you think the program starts. Well, we know where the program starts because it was that reset vector that we looked at earlier in the MiniPro, software. So A9 was the first location, and all we have to do is right click that and tell it that we want to tag address as code start point. And this will tell the disassembler, right, this is where you have to start decoding from. So let's do that. Okay, I'll just zoom back again. Right. Now this has changed again, so now we've got A900, which is correct. The next instruction was 8D0020, that's correct. And then there's other information after that, other instructions after that. Now what this has done is it's interpreted the instructions and put them into the correct lengths of fields. So A900 is, if you like, one instruction in one data field. The next instruction is 8D, which is the store at address, and it knows that it's 3 bytes long. You see that? So the first one, I'll see if I can zoom a bit more. So the first one is 2 bytes long, and then the next one is 3 bytes long. The next instruction is only 1 byte long, and with the 6502 I think that's the only options you get. You get 1 byte long, 2 byte long, or 3 byte long. That's kind of it. I don't think there's anything longer than that on the 6502. So yeah, so it's figured out what the lengths are and it's put it into a nice sort of decoded length, and you can start to see what the instructions are better. There's another one there, another 8D with address 0704. If you remember, these are reversed, so that's 0407. That's actually the address for that one, for instance. Now the other thing that it's done is it's given us some mnemonic code here, some assembler if you like, and instead of saying A9 it's now LDA, which means load into the accumulator, and instead of 8D here it now says STA, which is store at address, things like that. So this is nice, it's slightly more readable. You don't actually have to remember what all these numbers mean now. You've now got it in some kind of 3-letter coded language if you like, or it's closer to English. So here we go. So LDA means load to the accumulator, and the data field, if you remember, was 00, and there it is there. So this is the instructions, and this is the data or address. Now the hash here, let's see if I can get a bit closer. So that the hash here means it's an immediate instruction, which means this data goes straight into the accumulator, and the dollar means it's hexadecimal. So that means load immediate with the hexadecimal value of 00. Now we kind of knew that because we were looking at A900 earlier on, and we already knew that's kind of what it was doing. So this is a simple example, but it does make life a little bit easier because we can now see at a glance what this is doing. The next instruction, STA, which means store to an address, means take whatever's in the accumulator, and you remember we've just made that 0, so whatever's in the accumulator, and put that into address in its hexadecimal there, 2000. In hexadecimal speak, you know, strictly speaking, you shouldn't really call it 2000. That's a decimal number. If you say it properly, it's 2000. But you know what? A lot of people just do it as a shorthand because you know what 2000 looks like. So I thought I'd just point that out. So that takes the contents of the accumulator and puts it at that address. Now I happen to know, because I've already done a bit of work on this, I've happened to know that address 2000 is actually the port. There is a couple of chips on the input and output ports which both map to the location of 2000. So what's happening here is we're taking 0 value and we're storing it to the port, and that basically clears all the pins and it puts everything to a low state. The output pins, which drives the hardware on the analog board,
So what we're doing really is initialization. This is what we're doing. We're sort of saying, okay, clear all the port pins. That's kind of what these instructions do here. Okay, now you could put a comment in there. You know, I'll just zoom out slightly. I'm still getting used to this. You know, you could put a comment in there. In it the port pins. There you go. I could stick that in there. Yeah, so because we kind of know what this is doing. So there's our first little bit of information. There's our first comment. Init the port pins, and it actually inits them to 0, to 0. Okay, there you go. So we've already just figured out what these first 5 bytes, if you like, what they're doing. But the disassembler has helped us because, you know, we don't actually have to do the reverse in our heads of the address. It's doing it for us, and we don't have to know what A9 or A-D stands for anymore. It actually gives us the mnemonic, which makes life a whole lot easier. And you basically continue down the list, and CLC, that means clear the carry bit, clear other stuff as you go, and you start to hit other parts of code which do other things. Now the other thing worth pointing out is you'll notice we've got these labels here. These are classed as labels up here, and if you highlight it, you'll see it highlights to that one and that one here. So there's a couple of labels here, and these are branch instructions. BNE, which means branch if not equal to 0, so something wasn't 0, whatever we're doing previously. It means branch from there to there, and there's another one here, another branch if not equal from there, which is L1613 to here, L1613. So this is a kind of a loop. You can see, well, we've got a branch to here and we've got another branch to here, just by looking at these labels. And in time, it does take time. It doesn't automatically go, you know, boom, there's the answer, full source code with comments and labels and everything. It's not that clever, but it really gives you a good head start, and you can start to, you know, it still takes time, maybe it's a few hours to go through this, but you know, you can actually figure out where all of the labels and what they do, what the purpose of the labels do, and then you can start to change the you know, the names here. You can alter these labels to anything you like. If I scroll down a little bit, here's a one here. You see this one here? It says 1642, L1642, and here's another. L just means label, and here's another one, L1642. Now this is a very small jump, or a very small, if you like, loop. You can see it's some sort of a loop going on, or a decision. We've got another branch if not equal instruction, and we're jumping from here to here. So this is like a, if you like, a 2 byte. We've got this DEX, which stands for decrement the X register. The X register in the 6502 is a bit like the accumulator. It's an 8-bit byte within the chip itself. General purpose, you can use it for anything you like. So what's happening here is, just above that, in fact, we've got LDX, which means load X, and we've got an immediate value of FF, which is in decimal, that's 255. So we're saying, okay, load it with FF, that's the X register, load immediate. Then we're saying decrement the X register by 1. So instead of it being 255, it's now 254, or FE. Then we're saying branch if not equal, in other words, it hasn't hit 0 yet, from there to there. And you'll see that just means do it again. So take another 1 away from the X register. So now it's 253, if I've got if I'm remembering that correct. So it's going down 1 every time. You're subtracting 1, and if it's not equal to 0 yet, then jump back again. So this is a very tight loop, and it doesn't do anything else. And I can happen to tell you what this is. It's a delay of a very small amount of time. It basically tells the processor waste some time, you know, like a millisecond or whatever it is, and just stay in the loop, and then once it's finished, once that time has elapsed, the BNE, branch if not equals, is then not true. In other words, it is equal. So then what happens is you drop through and you start to do the rest of the execution of the program. So we know basically what this is just by looking at it, and we can give that a name. You can rename it. So instead of having a silly number of 1642, which means nothing, you can say small delay loop. And it's usually, my bad, it's usually a good idea to connect them up and don't have gaps in and stuff. Small delay loop, okay? Click that OK. Now you'll notice that it's actually changed both of them now. So you now can see at a glance this is a small delay loop. And you could even give it like a comment. Tight loop. Waste some time. Okay. Tight loop, waste some time. So not very computer speak, but you get the idea. So that's exactly what that's doing. Now that's just one example of a little bit of code, which to be honest is actually fairly straightforward to see. You can see immediately what's going on there, and you basically have to work your way through the whole program and look at other labels. Where does this one go? Well, this one goes to there. There's a branch of equal statement that goes from there to there. That's a branch. And then what does that one do? Well, that one goes down right down to here, which is L1653, another branch if not equal. And slowly, it does take time. Like I said, it's not an immediate result when you do this process, and it does take a bit of skill because you've actually got to figure out what the code is doing. But now that we know things like, well, you know, that's a port value, this is a small loop, and what have you, you can slowly start to see the picture of what the software is doing. I'll just come out a bit. That's the whole thing. So you can work your way through the code, change the labels, and slowly figure out what the code is doing. Now, just to save a load of time, of course, like what they see on television, here's one I prepared earlier, and we'll jump to the version that I've been working on. I'll just close this one, and we don't need to keep that, and I'll open up the one that I've been working on. So here you go. Here's about, I don't know, 6 hours worth of work, possibly a day. It does take time. You'll notice I've got like a load more comments at the top now. I've filled in a few things that I've basically figured out by looking at the hardware, looking at the card itself, and figuring out where the decoders work. If you trace the hardware, you can see how the decoder is working. Make a few notes on a bit of paper with a pencil, and basically figure out where the blocks are, where the page map is, just by looking at the hardware. And by doing that, you figure out things like this. You've got, let's have a look at it. You've got RAM, which is at the very bottom of the code space, which is from location 0 to 800 hex. That's a 2K RAM chip. It's actually a 6116 chip itself that we're using in the board. But what's important is the position of it. It's at the bottom of the code space, 0 to 800 hex. Okay, that's good, that's useful. Then we've got the ROM, which is the Eprom. In other words, the code that we're looking at right now is saved in this Eprom, and you'll see that it's mapped from 800, I beg your pardon, F800 to FFFF. So that's the 2K space that the ROM is occupying in the circuit after it's been decoded. F800 from to FFFF. So that's good, that's telling us where the chip's located, the EEPROM. Then we've got this here, which is, you'll notice these are all comments, these are semicolons, which means don't do anything, it's just a remark. This is purely for our benefit, and has nothing to do with the code whatsoever when you see these semicolons. Then we'll have this one here, which is port, and that's located at 2000 hex, which we kind of already knew earlier on. So yeah, port at 2000. Now then you've got this, which is I've written in here just RAM variables, at 0400 to 0408 hex. Now 400 to 48, you'll notice, is within the RAM location. It's actually slap bang in the middle, you know, from 0 to 400, and then from 400 to 800, it's right in the middle of the RAM. And we're hardly using the chip. That's a 2000 byte chip, it's a 2K byte, and we're only using 9 bytes, which is 0 to 8. So we're only using 9 bytes of a potential 2000. So it's pretty wasteful. I dare say the chip could have been replaced with something much smaller and it still would have worked. But I seem to remember at the time the 6116 chip was pretty cheap, so I thought it doesn't make any difference, we'll just bung one in. And it kept everything 2K big as well, which was nice. Plenty of room for expansion, loads of space left. So we're only using 9 bytes here. But we've managed to identify from those 9 bytes, just by working through the software and looking at the hardware, mainly looking at the software to be honest, what these bytes are doing. And this takes a bit of time just to go through the thought process of how the software was written and what's happening, and eventually you can figure it out, and you can figure out what these locations do. So at RAM location 0400, you know, we've figured out, well, this is an overs count, and I've written a comment in here, which is good. Counts overs before sending ID with no mute. So every time somebody transmits and then they leave go of the mic for the next over to pass it over to the other operator, they always leave a pip, like a little sound, which sounds what we refer to as a pip, and then the other operator can start transmitting. Now what happens there is we are counting the pips, we are counting how many overs there's been, and there's a reason for that, because after about 5, I think it's 5 pips, 5 overs if you like, the repeater automatically sends its CW ident, its CW call sign, and that's for identification purposes while the repeater's in use and you're passing it backwards and forwards between operators. Okay, so that's what that's actually doing. It's counting the amount of overs count. The next RAM variable is pip count. How many pips sent when there's no RX, when there's nothing actually happening, when everybody's finished the conversation and the repeater's just been left to switch off. It counts how many's been sent, and if that reaches a certain value, I think it's about 8 in this particular case, then the repeater will switch off. It gives its CW ident and then it goes to receive. It stops transmitting. So this is a kind of a bit like a timeout, but it's counting the pips to see that, okay, nobody's using the repeater, shut down. That's what that one's doing. Then you've got these 2 bytes here, which is timeout low, timeout high. These work together as a 16-bit byte, a high and low byte version, and these are timeout low and timeout high. These work together to form a longer timer, and this is so if somebody is transmitting but they're transmitting for too long, they're talking away, yes, it happens, the repeater will time them out and cut them off. So you don't want people rag chewing away, talking away for too long, and it will cut them off. And this timeout is a timer, if you like, a counter to see when that time has elapsed. And in our case, I think it's about 2 minutes. It's set to about 2 minutes. So this is a time check of about 2 minutes. And once this has expired, the repeater will again switch off. Then you've got other things as well. I won't go through them all. Pip delay time, mute flag, Morse pointer, the position of the data table that's reading the Morse. And there's also beacons as well. Now the beacon is interesting because it is another 16-bit timer with a high-low byte section, and what that does is it just simply counts for a certain amount of time and checks whether the repeater has been idle for a certain amount of time. In our case, it's set for about 10 minutes. And what happens there is if the repeater is not in use and it's just sitting there doing nothing, it will automatically give out its beacon CW identification every 10 minutes, and that's all it does. So this is like a 10-minute timer, if you like, and it gives out its beacon, which is a CW ident, every 10 minutes. So this is very useful because now we've got human readable labels, if you like, given to these addresses in RAM and the port at the bottom there. It's very good. It saves a lot of time. So just scrolling down a bit, here's our code. You'll notice the very first position, which was our A900, which means load the accumulator. We now have a label here called start. I'll put that in because we know that the reset vector takes us to this byte. So this is the start of the code. We've also got things here. Now, instead of it saying hex 2000 address, we've now got this human readable word port, which is identified up here. There's 2000 there, and it's now port. This is much better because now we're not looking at numbers, we're looking at words. We can see what the purpose of this address is. It's now a port. It's not a 2000, which could be anything. So yeah, it really makes life simple being able to put in labels, and this is one of the advantages with using a disassembler when you're doing reverse engineering, is that you really can put in your own labels that make sense. Okay, start code from reset. Well, we knew that. Init write port equals 0. In other words, set all the port pins to 0, and clear all the flags. These are all flags within the processor, and these are all cleared. So really what we're doing is initialization code here. This is basically setting up the processor into a known state and clearing the port pins. This is very typical of when you hit a reset situation on a processor. The first thing you'll always do really is set up your initialization and get the chip into a state of a known state, if you like, before you start to doing anything after that. So this is basically all initialization. And now that we know a little bit about the beacon and what have you, we've got the beacon low time and the beacon high time, which is these two values here, which equates to 0407 and 0408. The beacon times form, as I said earlier, the 16-bit location, memory location. And I've done a little bit of calculation here. Beacon low gives us 2.55 seconds, and beacon high on account gives us it's about 10 minutes 51 seconds, and that's the beacon total. The total beacon time is 10 minutes 51, which is exactly what we want. These values here set this up, the immediate hex of A7 and the immediate hex of FF. These two values here set the beacon time. So if we altered these times, we can see that now it will change the delay loop that's happening here, the delay time. Well, we're actually not doing a loop here, we're just setting it up, and we're initializing before we start to do the loop further down. We can set the time of the beacon. Well, that's cool. It means you can have the beacon anything you like up to a certain limit. It'll only go up to a certain delay length, but you know, you could make it a bit shorter, or you can make it a bit longer. So that's all good. Again, we've managed to change some labels. Instead of it just saying L XXX or whatever, we've now got tone check loop. Now the tone is the signal from the PLL detector on the analog board, and that's detecting the presence of a tone burst. Now, analog repeaters used to work like this. If you're familiar with, if you're a radio ham, you'll know all about this. Used to have a tone burst, which had to be sent with the audio signal, and it was a frequency of 1750 hertz or 1.75 kilohertz. That tone had to be sent at the beginning of your transmission in order to open up the repeater to activate the repeater. If that tone wasn't present, the repeater would not activate. Even if you were talking and you were pressing the mic, it wouldn't activate. It was a kind of a safeguard to stop against faults or all sorts of problems that you might have, interference, trying to activate the repeater. if that tone wasn't there, it would reject it. It was quite a good system for a long time. However, these days it's all been superseded by using CTCSS, a sub-audio frequency below 300 Hz, and that's constantly transmitted with your transmission. So it kind of does things differently these days, but at the time this is how it worked. It actually detected for a tone burst, if you like. Yeah, it was a decent enough system for a long time, but no longer with us. Now that's what this is doing here. We're looking at the port. LDA means load into the accumulator, so we're loading the value of the port, and the port pins are connected to the analog board, and that's detecting things like the squelch signal from the radio, from the receiver, and it's also checking for the tone detect. So there's a couple of pins there that we're checking for. We're doing an AND, a logical AND here of the value 0, 2, which means tone detect. That's the pin that we're checking for on the port for the tone detect. And we're doing check tone. We have a signal, we have a tone signal. Okay, branch if equal. Now if it's not equal, then do some other stuff. We've got a delay here. Okay, so you can roughly see what's going on here. We're checking for a tone, and if it's there, branch out somewhere. And if it's where we're branching, we're actually branching down to here, check tone, and it's actually starting to switch on the repeater and do other things. So yeah, I think the point we're trying to make here is that, we've come from a raw binary file from the 2716, the Eprom that we're using, and we've managed to read it in using the MiniPro software, actually copy the data from the chip into the computer in a raw hex binary format. And then what we've done here is run it through the disassembler, and within time worked out what the parts of code are doing, given them labels, labeling all of the addresses, and giving them human readable names, and slowly we'll build up a picture of what the software's doing and how it works. And then eventually you end up with something like this, which does take time. You have to stick with it, and it takes a little bit of skill, but in time you do figure out what everything's doing. Here's an interesting piece of code here, which I'll just point out before we close this, and this is the send Morse code ID subroutine. I've even put a note in there for my own benefit. Okay, so this part is actually a subroutine, and you'll see up here there's a JSR which jump to subroutine, and with the label of Morse, send Morse, which equates to here. So this bit of code here means call this, okay, and do all this stuff down here. Now this is interesting because, well, I think it's interesting anyway, because this is the part of the code that actually sends the CW, the call sign of the repeater. Okay, and we've got things like turn the port pin on, turn the port pin off. We're sending basically dots and dashes here. Now you'll notice there's a thing here called data table, fetch element. Now an element I've referred to as either a dot, a dash, or a space, or a stop bit. So we're reading a data table here, you can see that, and a data table, I'll just scroll down a bit, hang on, where am I, is here. There's the label there. The data table starts right here, and I've even put a comment in that says call sign data. How convenient. So a data of 5, the way that we've actually written the software up here in the subroutine is 5 is a space, like a gap. So it doesn't do anything, it just waits for, whatever it is, like 50 milliseconds or something like that. It's a fairly small delay. Just put a gap in between characters, between elements. So got a couple of gaps there, just basically waste a bit of time, a little bit of a delay. Then we've got this, which is a 1, a 0. Okay, now a 1 is decoded as a dash, so that's a dash, and then we've got 0, which is a dot. So that's dash, dash, dot, Well, that's a G in Morse code. Then you've got a space, leave a little gap, dash, 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 dash. That's a 0, and then leave a little gap. Can you see where this is going yet? And so on. This is my call sign. This is G0 B, which is da did it, space Z, which is da did it, and space, and then da did da. Where am I? No, I've missed a bit. Yeah, sorry, I'm scrolling around and it's not following me. Da did da da. So that's dash dot dash dash. So that's Y. So we've got G0 BZY. That's what that says. And then you've got a couple of spaces at the bottom. In other words, just waste a bit of time. And then you've got this, which is a 9. There's 2 9s here. You don't need 2 9s. I just put 2 in for whatever reason, a safeguard, I suppose. Why not? You only need 1. And when you hit the 9, it means stop. That's the end of the CW ident. And that tells the subroutine we're finished. And then get on with other stuff. So yeah, that's the data table for the call sign. We know that by looking at this. And there's a little bit of space at the bottom. You'll notice there's some blank area here. Could actually have extra digits in there. But my call sign is just 5 characters long, so it stops there. Yeah, so that's fairly interesting. That's what we're looking at there. That's the whole data table there. And you'll notice at the very bottom of the assembler code here, we'll have this bit here. Now these are the reset vector bytes at the very top of the code page, if you like. And the highest is an IRQ, which is this 16-bit byte here. Then you have the reset vector, which is FE00. Remember we saw that earlier. And then we've got the non-maskable interrupt vector, which again is just set to 0. We're not using the IRQ or the NMI in this circuit. Yeah, so I'll just come out of there. Now if you go to FE00, and I'll just scroll up here, right at the top. If you go to FE00, there it is there. FE00. You'll see this is our start. So yes, the reset vector basically takes us right back to the beginning. And that's kind of it. I don't know what else to say about that, but that's generally how we're using the disassembler to, if you like, recreate how the software works in assembler language. These are assembler mnemonics here. This is all assembler language, which you could actually run through a compiler and end up back with the original binary if you wanted to. You could make adjustments here. You know, this reset time low, you could change the value A7 to something else like FF or something like that, and then you could recompile it, and then you could change that value, put it back into the chip. So we've got control over the software now. We can see kind of how it works. So that's kind of as far as I've gone with this project, and I probably won't need to go any further. You could take this further. You could draw a flow chart. You know, you could take all of these loops and put them into boxes on a on a CAD package or on a piece of paper with a pencil even, and draw out a flow chart, and then you would see the overall operation of the software. You know, why decisions are being made, where all the delays are, and how you're turning pins on and off. So you could actually go further than this and put it into a flow chart. You could go further again and you could actually convert this into a C program or a C++ program. Probably just straightforward C would do this, and you know, write out the whole thing in C language, which is obviously a higher level than what we're doing here. But we've already gone probably far enough to be able to see how the program works and make adjustments if we wanted to. We're now in a position to make changes and maybe even enhancements, you know, add extra functions and stuff. We could do that now because we can see how it works and where all the labels are. Recompile that and put that back into the chip, and you've got a version 2. So I hope this has all been clear enough. It's quite a bit to take in if you've never done any reverse engineering of software before, but hopefully you can see the kind of thought processes involved, you know, changing labels, figuring out what the values of things do and then give them labels again, working through the decoder on the hardware, looking at the schematic and, you know, reversing the, you've got to reverse the schematic diagram of course, but it's not too difficult when you're working with standard chips like 74LS138s and things like that. You know, you just look at the data sheets and you can figure out where the decoding is taking things, and you can figure out where the RAM is, where the ROM is, where the ports are, all that kind of stuff. Yeah, and then you end up with something like this, which is you know, a lot better to read than a big table of hex, which is quite, you know, it's quite a lot to take in. So I hope this has been useful in seeing the software reverse engineering process using a disassembler, and I think we'll leave it there for now.